Good morning, everybody, and thank you for joining us for today's webinar titled Find Your Fit, Selecting the Best Simulation Strategy for Your Test Cycle. Today we will compare different coupling strategies for simulating long transient profiles. We will examine popular approaches and compare the accuracy, speed, and computational costs of each method. My name is Cassandra Wagner, and I'm the Director of Marketing here at Thermal Analytics. Our presenter for today is Lauren Tetzloff. Lauren started working at TAI as an engineering intern, but after receiving her bachelor's degree in mechanical engineering from Michigan Technological University, she joined our team full-time. Lauren provides support to customers and their projects, specializing in underhood and underbody simulations. If you have any questions throughout this presentation, please submit them in the questions box in the side panel of GoToWebinar, and we will work to answer them at the end. Don't forget, we are also recording this webinar and will be sending you the link following this presentation. Lauren, if you are ready, we can begin.
Thank you, Cass. Let's get started. When we think about the Model T, people do not usually compliment its comfort or groundbreaking design. They think about the process that allowed it to be built on a production level. The process is what people remember. When doing thermal management, the process is also very important. Let's look at the thermal management process. We have our source inputs, meshing, model construction, calculation, post-processing, revision steps, and then finally communicating results. It's important to minimize resources when we can, which can present themselves in many forms: man-hours, computational costs, and software costs. Thermal management as a process allows us to use manufacturing principles to optimize the process with our existing understanding, and the ideal process minimizes the cost of each step. Then we need to look at what is the most effective thermal management process. It needs to support production work, easily adapt to new jobs, and minimize resource requirements. We will examine the calculation step in the thermal management process. With that in mind, the remainder of this presentation will discuss a comparison of several simulation methods for conjugate heat transfer simulation. Now let's talk about finding your fit. And in this presentation, we'll focus on the calculation step. So you will select your drive cycle, your model geometry, and then your method to ultimately determine your fit. In this presentation, we will be examining which method would be best for the fit. And just like people like different cuts of jeans, many different factors are important to different engineers. So with fit, there's usually no one-size-fits-all approach. Today we will be first looking at the simulation methods, then we will go through the approach to evaluation. We will then look at some results and highlight some conclusions. The different strategies that we will be looking at today include conjugate heat transfer, stepwise, pseudo-transient, 1D surrogate, and 2D surrogate. First, there's the conjugate heat transfer solution. This solves as one solution and is very detailed. For this presentation, this will be the baseline that other studies will be compared to. The rest of the studies use CFD coupling. They use titherm to calculate the heat transfer via radiation and conduction, and CFD to calculate heat transfer via convection and advection and predict flow patterns. The titherm model will then pass surface temperatures to the CFD model, which will solve and pass convection coefficients and fluid temperatures back to the thermal model. The first method that we will look at is stepwise coupling. The process couples a structure to steady flow. First, wall temperatures are sent to the fluid domain at the end of each coupling interval. The fluid solution solves and then sends heat transfer coefficients and fluid temperatures to the structure domain. The next period is then initialized with the wall temperatures of the previous. The transient structure model is solved, and then this entire process is repeated for the duration of the test cycle. The next is pseudo-transient coupling. This process also couples a structure to steady flow. So let's take a detailed look at one of these coupling steps. First, the thermal simulation is run with the initial CFD data. Then wall temperatures Wall temperatures are then sent to the fluid domain. The fluid model is run, and this computes new HTC and fluid temperatures, which are then passed back to the thermal model. We then run the thermal solution again, which creates a new wall temperature, which is passed back to the fluid domain. This solution then solves again, which creates new HTC and T fluids, which are passed back to the thermal model. Finally, the thermal model is run again, and this process continues until convergence is reached, and then we will advance to the next coupling interval. And again, this process is repeated for the entire cycle duration. Last, we have our surrogate approaches, 1D and 2D. For the sample range of vehicle operating conditions, the 1D model sampled vehicle speed. The 2D model used an optimal Latin hypercube of the vehicle speed and inlet temperature, and what this did is combine the two inputs of vehicle speed and inlet temperature into one polynomial. Both used coupled conjugate heat transfer solutions to calculate the sample points. The interpolation scheme used for the 1D method was linear interpolation. The Gaussian anistropic Kriging approach was used for the 2D surrogate. For running the transient thermal models, the 1D surrogate method used existing software features, while the 2D method used a custom coupling harness. Let's take a brief look at the pros and cons of each of the methods that we just discussed. For the traditional conjugate heat transfer simulation, we have very high accuracy and an easy process, but the cons include large computational costs and inflexible resource allocation. The stepwise transient allows us to have a reduction in computational costs compared to traditional conjugate heat transfer and more flexible resource allocation. The con is the steady-state fluid assumption. The surrogate models have lots of benefits, but also lots of downsides. We see reduced runtimes, especially for very long transient models. The surrogate we create can be reused. It allows for flexible resource allocation and flexible post-analysis options. The cons include that it can require a lot of sample points, it's a very complex process, and the steady sample point assumption. Last, the pseudo-transient approach also gives reduced runtimes and flexible resource allocation, but it is a complex process and has a steady-state fluid assumption. For the two processes here that have complex processes as a con, thermoanalytics has a solution, Cotherm, which is a process automation software. So if we look back at the thermal management process, Cotherm can help minimize the man-hours of model construction, post-processing, and model revision, while also allowing for flexible resource allocation with the calculation. And these are these steps in the thermal management process. All of the methods that I just described were completed in Cotherm, but the following two examples that I'm about to show are already ready available templates that you could use today. First is the drive cycle extension, which models the 1D surrogate. The inputs that the user provides to this method are the thermal and CFD models and drive cycle data. Cotherm then takes care of determining the coupling points based on the drive cycle profile, running steady thermal CFD cases, importing the CFD results into the transient thermal model, and running the transient thermal model. This gives one output of the transient thermal model. The next is the pseudo-transient method. The inputs to this include the base thermal and CFD models, boundary conditions, and the coupling interval desired. Cotherm then takes care of setting up the steady-state CFD models, coupling the thermal and CFD models, and then merging the thermal models. This gives one complete output of a merged thermal model with all the CFD points. The approach used today to compare the methods include using a simplified geometry of an engine bay. The mesh sizes are stated here, and the mesh was kept constant between all methods. The sources of heat for this model include the head, manifolds, block, and crankcase. Each has a defined H&T that drives the temperature. Last, there's one inlet and two pressure outlets. At the inlet, there is a defined speed and temperature. The three drive cycles that we will compare today vary in duration, max speed, and vitality. This allows us to see how the different methods perform on a range of cycles. First, let's look at the results from the conjugate heat transfer solution. On the top, we see the velocity results, and on the bottom are the temperature results for the three respective cycles. As expected, the results show high inlet velocity, high velocity over the engine, and a low velocity behind due to the low pressure outlet. All right, now let's look at how the methods compare. First is the stepwise transient prediction. On these graphs, the conjugate heat transfer solution is shown in black, the vehicle speed is shown in gray, and then the stepwise solution using a 30-second coupling interval is shown in green. As we can see, the two dynamic cycles predict or show a slide over prediction. And the low vitality case shows a consistent underprediction, which is cycle 3. These temperatures were taken from a 6-node average located on the manifold. Next, we'll look at the surrogate modeling methods. Again, in black, we have the conjugate heat transfer solution. In red is the 1D surrogate, and blue is the 2D surrogate, and in gray, again, is the vehicle speed. We see a consistent overprediction of temperatures for both the 1 and 2D surrogates, but they do perform better in cycles 1 and 2. Last, we have the pseudo-transient prediction. Again, we have the conjugate heat transfer shown in black and the pseudo-transient shown in orange. And these, again, are all taken from the 6-node average on the manifold. The two dynamic cycles perform better than the non-dynamic cycle, and cycle 3 shows a consistent underprediction. Okay, let's look at these results in more detail. On the plots shown, on the top, we're looking at the same manifold temperatures that we were viewing in the graphs, and in the bottom graph, it's looking at a 55-node average taken from the top wall. And these plots show the different cycles and their different root mean square errors. So we see the 1D surrogate, 2D surrogate, stepwise with the 30-second coupling, and pseudo-transient with the 30-second coupling. So as we can see with the total accuracy on the right, the stepwise overall with averaging between the three different cycles is the most accurate, followed closely by pseudo-transient and then the surrogate methods. But overall, the accuracy of all four of them is fairly comparable, being within around 2 degrees. Then let's look at the computational costs of running each method. So again, we see the surrogate methods, the stepwise, the conjugate heat transfer, and the pseudo-transient method. The 2D method does shows a significant increase, and this is driven by the custom harness overhead. But soon a 2D option will be available in Cotherm, which will greatly reduce the overall time. And then on the right-hand side, we see the total compute cost of all the methods together. So the 1D surrogate is the fastest overall, followed closely by the stepwise and the pseudo-transient, and all show significant cost savings over the traditional conjugate heat transfer solution. Another way that we could look at this is if we're trying to find our fit. We could look at the CPU hour per second on the x-axis with the RMSE on the y-axis. And this could help us determine which modeling method may be best for us. So we can see that all three cycles are shown on this graph, and we see different clusters around different accuracy and time. Now, if we just look at results from cycle 1, and as an analyst, maybe we are considering a certain threshold for how long we want the cycles to take, as well as a certain accuracy that we are interested in. And so this can narrow down which method may be the best for us. And in this case, the 1D surrogate method and the stepwise coupling would both be good answers to finding our fit for this particular model setup. It is important to remember that this is just one model setup and that your fit may be different. The last thing that we looked at was using different coupling intervals with the same cycle. So these are all taken from cycle 3 with the pseudo-transient prediction. We have the 30-second coupling interval that we saw before, and then we have an additional 60-second coupling interval, 120-second coupling interval, and then a manual approach where we selected the coupling points based on the boundary conditions. And as you can see, overall, the results are very similar. Again, we'll take a closer look at the manifold and top wall temperatures for the different methods. If we look at the total accuracy over all the methods, we do see that the manual approach where we selectively picked the points, we see a slight increase in our root mean square error, but overall the results are very similar. The scale on this y-axis is very close. Again, if we do a different approach with looking at these results, on the x-axis is number of coupling points, and the y-axis is the root mean square error. And so this shows that with the manual approach, we can have a fewer number of coupling points, but still maintain a high level of accuracy. Another way to look at these results are the total solve time with the different methods and how this is broken down between the thermal domain, the CFD domain, and then the sample point computation time. These are all looking at results from cycle 3, where we did the different number of coupling points for the pseudo-transient method. And it's interesting to note how with the pseudo-transient runs, the CFD runtime percentage decreases as the coupling interval increases. Now let's look at some conclusions. We saw that there was a significant cost difference between the methods. The stepwise and pseudo-transient coupling offers a good balance of accuracy and runtime. Finding the correct number of coupling points that balance accuracy and computational costs is very important. And the surrogate models offer significant savings but sacrifice accuracy. Some future research that will be considered would be the size of the model, different time stepping, other coupling methods, the sampling method for the surrogate model, and surrogate model interpolation methods. Today we've gone over a lot, and the fit for every situation can be different, so contact us today to help determine yours. Thank you, and are there any questions?
Thank you, Lauren. So we do have time for a couple questions. So the first one that came in was, how long did the different methods take overall?
Okay, so the pseudo-transient and the 1D surrogate methods took around 2 hours. The stepwise method took around 3 hours. The 2D surrogate took about a day, while the conjugate heat transfer method took multiple days. And the reason we looked at the CPU hour per second was just to standardize the time, since some of the methods were run on a different number of processors.
Okay, and then last question here, how was the 2D surrogate model run?
The 2D surrogate model was run using Cotherm with the custom coupling harness built into that. And actually all of the methods were using Cotherm, but only the 1D surrogate and the pseudo-transient methods are using templates that are available today to make the setup much simpler.
Okay, so thank you everyone for attending today, and thank you, Lauren, for your presentation. Remember that any questions that we didn't get to today will be responded to via email within the next day. Thanks again for participating in today's webinar, and have a great rest of your day.